So for the first one is about the displacement, speed, velocity, and acceleration. I think you can find those from the textbook.
Yeah.
Displacement, yeah, is meaning the position change. Speed is the change of position over change of time,
Uh-huh.
but without a direction. Velocity is the change of position over change of time with the direction. Acceleration is change of the velocity over change of time. So that's some basic definition about that.
And one more question before you start. Since you're recording this, can you send it to me after or no?
I probably will just post the link that you can actually,
Perfect, perfect. So I could go over it.
yeah.
Okay, so displacement v. Okay, I'll find them. Then can an object have a non-zero velocity and a zero acceleration? If so, give an example.
Mm-hmm.
Can an object have?
So you certainly can guess, probably gives a lot of different kind of example, but the one I would think about is that non-zero velocity but zero acceleration, meaning it's moving but it's not accelerate.
So like at a
And
constant velocity.
yeah, so like a circular motion that we talk about, no, that one is not. That one actually has acceleration. If you have some object is moving with frictionless ground and without touching it, it's not going to accelerate, but it's just keep on moving. Okay. Can an object has an instant time that have a zero velocity and non-zero acceleration, which means velocity is equal to zero, but acceleration is not. This can be like a free fall things that if you throw an object go upwards at the peak of the object, um, it will have a zero velocity when it reach to the peak, but it still have acceleration. The acceleration is the g is 9.81, and that one is going downwards. So that is non-zero acceleration, but still but has a zero velocity at the peak. The number three, the Newton's law. I think we talked about this before. The first law of an inertia, and looking at the net force is equal to zero, an object either at rest or moving at a constant speed, constant velocity. The second law is the law of motion. If you have a net force, which means net force is not equal to zero, then the object will move along the direction of the net force and it will accelerate. The acceleration is determined by the mass and also the net force. The third law is the law of interaction, which simply means if you have an action, you always have a reaction. They comes in pair, same amount of the force, but opposite direction. Okay. So you did one of the exam problem talking about the tug of war. So
Oh yeah.
yeah, so if they are tied, that means the two force go opposite direction and they're like an equal amount, so it's equilibrium. So it will be at the rest. If one side pulling harder than the other side, then you're going to have the net force is not equal to zero. That means they are going to start to move toward one end. And the action and reaction you can explain like when you step on the ground, then there's a force pulling to the right, but the friction will keep you to the left. So you depends on the friction actually to give you the support that you can stand still without being pulling to the other side. So that's or you can another example for this case is that if you pulling the rope and the rope is actually pulling on you as well. So that's force is going to be the same, and that is also the action and reaction. So that will be number three. Number four, looking at the conservation. So if if you have a collision and the collision is on a level plate, a ground, so there's no change of height, and frictionless, that means there's no external force, then what will be conserved? Well, momentum is always conserved if there's no friction. So in collision, momentum always conserved without any of the external force. So in this case, there's no external force. So you can think about momentum is always conserved. Potential energy is also conserved in this case because it's a level ground. So a level meaning there's no change of height, so you don't have change of potential energy. Kinetic energy is not necessary to be conserved in this case. It depends on what kind of collision that you have. We have two kinds of collision in a very extreme case. One is the perfect elastic one, the other one will be the perfect inelastic. Elastic meaning when two things collide, they will separate right after. If they are inelastic collision, like perfectly inelastic collision, when one object hits to the second object, they will move together. Just like the one of the calculation problem that you did for the bullet and the block. When the bullet hits to the block, it's going to embed into the block and they move together. So that is what we call the inelastic collision. For the inelastic collision, most of the time energy is going to be lost. It can be lost in several different ways. One of the way is deformation, because you have to embed something into another object. You're going to deform the material. So that deformation takes some of the energy. So the energy in that case will not be conserved because some of the energy being used to do other things. Number 5, PT diagram, VT diagram, acceleration time diagram. These things, if you watch the kinematic review video at the bottom, and I did explain the difference of these two, and especially the velocity diagram. The velocity time diagram, if you look at the slope represents the acceleration. If you look at the area under the curve, it represents the position change. And if you have the position time diagram, the slope represents the velocity. Okay, the slope represents the velocity. So that's how you can interpret those graphs. And make sure that if you know what I mean, if you have constant, and constant meaning the value doesn't change, and if you look at the graph, it should be a horizontal line. That means something is constant, horizontal. If it change with time, and then they can change it in several different ways. If they are like a linear change, meaning you increase a certain percentage, and then the other property will also increase certain percentage, that will be like a linear relationship. Then the slope is going to represent the change of the property. Such as acceleration. Acceleration is the change of the velocity over time. So if the velocity time graph is a simple, like a ramp line, then this will be like this. So if you have this is a time, and this is a velocity, and this line here, if this is a linear, then the slope of this represents acceleration. Okay. An area under this one is what we call the displacement. So that's important about being able to interpret this kind of things. Again, the kinematic video talk about that as well, and some of your calculation problem also look at that. How will ask you how to find those acceleration. So that's something that you should read. Number 6, to draw free body diagram. This could be any kind of case. And when you draw the free body diagram, it simply identify the force. After you identify the force, then you combine with the Newton's law, and the Newton's law looking at either the net force equal to 0 or net force is not equal to 0. One of the things that we did in the lab, we did ask you to draw a free body diagram. Say if this is one of the bench, and we put a pulley over here. We use a wire to connect two objects. One object here going down, and the other object is going horizontally. And if you want to draw a free body diagram, well, this is also a good case, good chance to discuss about a lot of misconception when I grade your work, especially for the normal force. I don't know why some of you just keep on writing the normal force, even though there is no normal force exist. You have normal force only when you have contact with other object. The normal force is a contact force. It has to have a contact. Without a contact, then there's no normal force. So if you look at this weight on the right is hanging in the air, there's no normal force in this case. Okay, it has a weight, and the weight going down. And it has a rope connect to that, and then you have to isolate that. You have to cut the rope. When you cut the rope, you're gonna have a tension force. So the tension force is the one that going outwards. Okay, tension force going outwards. Normal force going inward, going into the object. So that's the case. This one doesn't have a normal force. Don't write normal force. If you write normal force again, then you're gonna have points off. In this case over here, the horizontal car, it also have a weight. So this is going to be the weight of the car. Weight is not the same as the mass. Weight is the mass times g. So I still see people make mistake using the mass as the weight or using the weight as the mass. So be careful about the words that you use, and be careful about the value that you use, and look carefully what they are asking for. Because this one contact with the table or the bench, then you're going to have a normal force. So that normal force is also known as the supporting force. So that will be into the object, right? So if you draw from the bottom, it go into the object. So this one is what we call the normal force. Beside this, in this case, also have a rope over here, the tension force going outwards of the object, so it will be in this direction. In this case, you can also look at the Newton's third law that will be applied to here. The third law tells us there's a action and reaction. So the rope that you see, these two T actually is kind of action and reaction. So they are opposite direction, and they're like same amount. So when things connect together, move together, their acceleration, their velocity should be always be the same. Otherwise, the rope will slack. The slack that you're not going to provide any of the force on the other sub object. So free body diagram could be anything. Then just make sure that you know how do we draw a free body diagram. We draw a free body diagram in many cases already. Number 7, you have two balls. You toss off the edge and of a cliff with the same speed but different angle. One horizontal, one 45 degree. So that's make a quick drawing. So here is a cliff. This is the ground. You toss two ball, one go horizontally, and there's another one they go with certain degree. This one is this one here. So two cases. Then we want to compare the potential energy, kinetic energy, and the time of a fly while it's airborne. So we want to compare, are they going to be the same? Are they going to be, one is larger? If the one is larger, which one will be larger? So and it also depends on where you look at. So if I look at here, if I look at these two objects at here, the red one, which has an angle, the blue one horizontally. And so if we start with the potential energy, do they have the same potential energy? And how do we define potential energy? Potential energy depends on the height. And these two start with the same height, and then it will have the same potential energy at the very beginning. So over here, your potential energy is the same. Okay. If this one started fry, and then you will see the blue one is going to the right, but it's going to have a motion look like this. It will bend down because there's a attraction from the earth. So at a certain point, let's say the blue one go to here. Does it change its potential energy? Then you have to ask yourself, do they change their position?
Yeah.
Do they change their height? Yes, so it will, right? And what about this red one?
It's gonna have a higher potential energy.
It will start to get higher and higher potential energy, but at a certain point, it will start go down as well, right? When it go down, it's going to, you're going to have the change of potential energy, but you're going to lose the potential energy because of the higher of the object, the higher of the potential energy. So if you go down, then we'll be losing potential energy.
But the higher potential energy, that means the more kinetic energy is gonna be, or?
Well, kinetic energy will be different things. So we finish the potential energy. If you look at the kinetic energy, that you're looking at the velocity. You have to look at what is the speed at that moment. Okay. If you look at the red one at this point, then the kinetic energy at this point is going to be equal to 0 because it's the highest peak the ball can fly to. When it reaches to the highest point at that moment, you are going to have a 0 velocity. And because you don't have any of the velocity, your kinetic energy will have, if velocity equal to 0, then kinetic energy equal to 0. If it's not, then kinetic energy should have some value. So over here, if you look at this one here, then we will say, the kinetic energy will be equal to 0. And the reason is because the V is equal to 0. Okay, so that's the kinetic energy. If these two start at the same speed, and then their kinetic energy and their identical object, then their kinetic energy at the beginning will be the same. The kinetic energy doesn't care about the direction. It's not a vector, so it's simply look at the value. And kinetic energy doesn't have a negative too. It's always going to be positive because the velocity square guarantee that potential, the kinetic energy is going to be positive. So moving to the right, moving to the left, even though the velocity has a different sign, but their kinetic energy is going to be the same. And if you look at the time of the flight, so time of the flight, then the first thing we wanted to know is which one stay in the air longer. And this is kind of like obvious, the red one, the one that was an angle, you shoot it with an angle that will stay in the air longer. What else? Okay, number 8, what's the difference between the static kinetic friction? Which kind of a friction helps a car accelerate? We have two kinds of friction, one static, one is dynamic. When things start to move, when things move, then you only use the kinetic friction. Static friction is normally that one is the maximum static friction that we're looking for. The maximum meaning unless you apply a force that is greater than that amount, otherwise the object will not move. One of the misconception people has is if things doesn't move, then there's no friction. The answer actually is wrong. The things doesn't move was because the net force equal to 0. It's not because of the friction force is equal to 0. And the friction force is the force actually counter to the direction of the motion. So the static friction is in the case that an object is not moved. But that also implies the static friction has a wide range of the value, because if you apply 1 Newton and object doesn't move, then you apply 2 Newton, object still not move, and you apply 10 Newton, this object still not move, then in these 3 different cases, what do you think the friction force is going to be? Well, it's always going to be, depends on how much forcefully you are pulling it. So if you pulling with 10 Newton, it doesn't move. That means your friction force at that moment is 10 Newton. If you're pulling 3 Newton, it doesn't move, then that means that your friction force is 3 Newton. But there is a maximum value. That maximum value is normally what we refer to the static friction force. It is the limit. When you go over that limit, the object will start to move. And we kind of explain friction by looking at the microscopically, what is the surface of the object looks like. If they are rough, and which actually is most of the common case, most of the object, the surface is very rough. And because it's a very rough, you have 2 objects and moving, so one of them is moving, there has to counter those, like a sharp edge from the surface of the other objects. And that's where the friction force is coming from. The friction force is actually, you have 2 things against with each other, you try to cancel it out, and was what happened in that case. One thing about the kinetic friction is the kinetic friction force is always going to be a same value. Static is not. Static can vary. The kinetic friction force doesn't matter how fast you are moving, it's going to be the same value. And it depends on the normal force and also the coefficient of the friction force. So that's about the friction. Which one helps us to move? Which one helps the car to accelerate?
I believe the static.
Yeah, it is static. So the static is actually the one that helps us to have the car moving. So you actually prevent the object going slide, and then you have to make sure that the car actually one end, when the end touch to the ground, that point doesn't move. Because that point doesn't move, so you make the rest of the thing moving forward. If the bottom part where you touch to the ground, the tire touches the ground moving, then you're kind of sliding, and then you're not going to provide the provide the enough force to make an object accelerate. So yeah, that's the static friction. Okay, which one we are? Number nine about the force and the torque. So we have a definition about the torque. Torque is the force times the level arm. So force itself is not torque. Force is the reason why things accelerate. When things accelerate, meaning it's moving along a direction, moving along a line. The torque is the lever arm times the force, and it is the thing that keeps things rotating. So the torque create rotation, acceleration, create a linear translation. So that's one of the main difference between these two, and it was the consequence of the force and the torque. How the net force on an object can be zero while the net torque is not. How a net force on an object can be zero. And the net torque is not. Okay, so if you give a force, and let's say, for example, that you have an object, let me make a drawing here. Here you have very short bar over here. If you give one force to this direction, so then you have a force, right? So let's say this is a force, and F represents the amount. At the same time, if you give another force, and this force has happened to have the same amount like that force, and we give that force over here, and they have the same amount. And if you calculate the net force, this net force will be equal to zero because they have a different direction, and direction is totally opposite, and they have the same amount. So you sum them together, you're going to get a net force equal to zero. But if you look at the torque is not going to be zero. And you can try this by yourself as well. If you push an object like a pencil on your table, and both hands push in at the same amount of force, but opposite direction. And what happened is the thing start to rotate. And then you create a torque to only make things to rotate, but the net force is not going to be, the net force is equal to zero, but it's not going to move in the linear direction. So that's the case that you can explain in this way. Okay, what else? Okay, number 10, what a factor affect the value of the rotational inertia? For inertia, to change that, you can change the mass. And the inertia is the I that we're talking about. So if you have a more of the mass, you're going to have a more of the rotational inertia, which means more of the mass is harder to rotate. Okay. What else? The other thing is one of the problem that you were given in exam 2 about the ice skater things when she or he change the position of the arms, you're going to change the moment of inertia. So the shape can also change the moment of inertia, not only just the mass. Okay. And the next part, you already did for the exam, so you should know what the answer is. Okay, seatbelt. This one is also your exam 2 problem. The key is the impulse is equal to the force times the time of the contact. Seatbelt give you more time of the contact. The momentum or the impulse is also going to be the same when you have a collision, and that one is not going to change. And what you can change is that you can change the time of the contact such that you can reduce the amount of the force they will against you when you actually had the collision. And if you give more of the time to slow down, and you will likely have less of the force acting on you when you hit to anything inside of the car. So that's why the seatbelt can save your life during the collision. Number 10, the factor affect the value of, wow, didn't I just say that already? Number 12. Buoyancy force submerged submarine. Why the buoyancy force on the submarine is greater than the buoyancy force while it is floating? The buoyancy force of submerged. Okay, so this is similar to the problem that we ask you in the lab. Things is floating, that you put cylinder in a cap and it's floating. Suppose that you put the cylinder all inside of the water. And why there's a difference of the buoyancy force and which one is larger? So if you think about if something floats and you think about the rule about the buoyancy force, when things float, the buoyancy force is the weight of the object. So the weight of the object is the buoyancy force when this thing is float. When the submarine is float, then the weight of the submarine is the buoyancy force of the submarine. If it's submerged, then we look at how much of volume displaced, and we use the volume of the water or the seawater to represent the buoyancy force. Okay, so that one is going to be smaller, and because if you think about the density of the object, if the object will flow, meaning the density is smaller than 1. If the object sink, that means the density is greater than 1. If you put the submarine fully submerged in the water, it actually try to go up because your buoyancy force is only like a density of the fluid times the volume of the submarine. That's the weight of the submarine. And the weight of the submarine when it is afloat is not the density of the water to times with the volume, is the density of the submarine to times the volume. So the density of the submarine certainly is larger than the density of the water, so that will make a difference. Okay, let's look at which one. Number 13. How do you determine the density of an irregular shape object? If this one is sink or if this one is float. Let's make a picture real quick. I have a container over here. I have an object which I don't know as an irregular shape. Because it's an irregular shape, it's so hard to determine its volume. And the buoyancy force is based on the volume, right? It's based on how much volume to be displaced by this object. So if you wanted to find the density of this object, then you have to know what does density depends on. Density depends on two things, depends on the mass, depends on the volume. And which means, how do I know the mass? For irregular object, you can still use a scale to measure its mass. So it's not a problem to get this one here. The problem is, how do I get the volume? Well, the volume is also simple. If this is irregular, if you fill the water full before you drop this irregular, you put another pen at the bottom, and when you put this one in, you just look at how much water being displaced by this object. Then you got the volume. The volume of the water is going to be the volume of this irregular shape object. So you can determine its density in this way. If things is float, then how do you make the prediction? Okay, so if you remember, go back to one of the problem in the practice exam 3 that we give you in a question saying how much, well, same thing for the exam 3, one of the multiple choice question asking about this. If you have an object is floating, and how much of the percentage of the object is submerged in the water, it depends on the ratio of the density. So the lighter of this object, the smaller of the density, the volume will be under the water. So the density of the object is actually can be determined by how much of water being displaced. So you can do like similar thing like this one here. They fill up all the water. Then you drop this one in. It's going to displace some of the water out. And you collect those water, then you will be able to determine the density of this one here. The density is going to be the ratio. See. It's going to be the ratio of the density of the object to the water. So how much the volume submerged is going to be whatever that you collect here. Let's say this one has the density 5/8. And the volume being displaced will be 5/8 of this total volume. And you collect, then this will represent like 5/8 of the volume of this object, and you simply just multiply 8/5, then you can get amount of the volume in this case. And the mass still, when you wanted to get the mass, you can still use the scale to measure it. So that's the difference. If you wanted to measure some irregular shape object, it's buoyancy. Which one? Number 14, fast moving air. What is the principle that will make this one to create a difference of the pressure? Well, that one is based on the Bernoulli equation. So if you look at the Bernoulli equation, if you have a faster speed and you're going to create 1/2 a rho v squared to be different. So Bernoulli equation has this one, this form P plus 1/2 rho v squared, this v is the speed, and plus the rho g and the y. This is going to be a constant. So if you have a fluid with the speed to be different, and the difference will create a pressure difference. And pressure difference will create a force. So if you have a net force is not equal to zero, then the pressure, the larger pressure will push to the smaller pressure. So that will create a pressure force due to this situation. And so the velocity is moving faster. When this is moving faster, this value will be larger, and the pressure of this one will be smaller. And if the velocity is smaller, then the pressure will be larger. So it will coming from the larger one to the lower one. And if you think about the airplane, so the airplane look like this. This is the wing of the airplane, let's say. And when you have the air blow against the airplane wing, some of the air going downwards, some other air going upwards. Now the going upwards one is going to travel longer, which means the speed of this air will be x over t, which will be larger. This has to move faster. And the bottom of this one here, the speed is going to be smaller because it travels with less distance, and the top one is more curved. So it will have more of the distance, therefore it has a more of the speed. So top one has a higher speed, bottom one has a lower speed. When you have a higher speed, what happened to the pressure? It will
Lower
be
pressure.
lower pressure, and the bottom has a higher pressure. So high push to the low, that's how the airplane can lift. Okay, number 15. Three-way of heat transfer. This is one of the questions that you did in the exam. Conduction, convection, and radiation. Conduction has to have a direct contact, especially for metal, for solid. Convection is due to the bulk motion of the fluid. So the fluid is flying at the same time to either carry in or carry out of the energy. Radiation is the heat transfer from the electromagnetic wave. We haven't talked about the wave, but this is one of the basic things coming out from this chapter. The radiation, everything has the temperature greater than 0 Kelvin will radiate. It's just the amount of the radiation and also the kind of a radiation, meaning the kind of a wave will be different. How our human being can, let's see. Oh, radiation, yeah. So then we want to explain why the restaurants serve a baked potato with the aluminum foil. So what are the kind of a heat transfer that you can think of from this situation?
From baked potatoes?
Yeah.
So my guess is like how the
Does
rate
it
like
has the prevention of the conduction?
no, I think it's convention.
Yeah, convention, because you kind of close it, then the heat wave cannot leak out. It will not be carried by the cold air. So convection solely is one thing. Could you have radiation in this case?
Uh, with the aluminum attracting heat, I don't think so.
Well, so if the potato initially is hot, right, because it was cooked.
Yeah.
When it's hot, it has a temperature. The temperature suddenly is higher than 0 degree Kelvin. So anything has a temperature will radiate. So the potato inside of the wrap is also radiate. You use aluminum foil. The aluminum foil is kind of shining surface. When you have a shining surface, you are going to refract the radiation wave. So that's why when you refract back, then you're not losing any of the energy from the aluminum oil. So you can prevent the heat loss in this case. So that's the how you can explain of this one here. Do you have a conduction heat transfer?
Conduction is like you said, like solid touches and it transfers the heat.
Yeah.
Mm, I don't think so. The aluminum foil would. Uh,
Yeah, in this case, we're
no.
not, because if you wanted to prevent a conduction loss, then you will try to use some material with less of a conductivity.
Like when we pour the boiling water into the cold water, right? Or is
No,
that
not a cold
convention?
water. We're talking about the conductivity, which
Conduct. Okay.
means, yeah, something will conduct heat faster or something will not. Like wood is not a good conductor. So it will not transmit, it will not make the heat to move easier, right? So that is the thing. But in this case, the baked potato, you don't have that. We don't wrap it around with the wood. We wrap it around with the aluminum foil. So it's not going to help you to prevent the conduction loss. But then conduction loss is when you touch to that object, right? Or you have some other object connect with that. So in this case, conduction is not the main thing that we will use to prevent the heat loss. Okay, 16 about the Doppler effect. So we show the Doppler effect at the last case of the last class. The Doppler effect is when you have either the source of the sound or the observer moving. Either one of them moving, then you will hear the sound will sounds differently. If they moving toward, if they're moving toward, getting closer and closer, then the frequency of the sound wave will be increased. If they're getting away, then the frequency will decrease. So that's the Doppler effect. Okay, so it happened either the source or the listener are moving. Um, and what direction that you can hear a higher frequency? Well, the direction is if they toward to each other. If they toward to each other, then you are going to have a higher frequency. So number 17, what is the wave interference? So wave interference meaning if you have two or more wave and you generate over a time, they're going to have an interaction between each other. Either they will have a constructive or destructive interference. If you have in a constructive interference, what I mean is the wave is going to be overlapped. They are going to be in phase, meaning they happen to start at the same time and end at the same time. And you add these two together, then they will have an amplified amplitude. And that is what we call the constructive. If you have a destructive, meaning the two motion are not in phase, and normally we will say this is the out of phase. If they are out of phase, then you're going to create the wave to be a minimum. because one goes up and the other one tries to go down. So you kind of balance the displacement, and it will be giving you like a zero amplitude or small amplitude if you put these two things in a correct way of doing that. The node and anti-node is this. So this one is related to the standing wave. So what is a standing wave? Standing wave meaning if you control how things is vibrating, and when you control it correctly, the vibration will like a freeze. It is still moving, but if you look at the object, and you will think that things actually stopped. It's not moving. And that is what we call the standing wave. So when you have a standing wave, and then we call several, like 2 or 3 different things with the terminology. This line here represents the horizontal equilibrium line. If you're using a mass with with um, with a spring, then this will be the position where they have equilibrium. When you let it go, it's going to move up and down, right? So when it moves up and down, if you have another side over here, which is a wall, what happens when this hits to the wall? It will bounce back, but amazingly, it's bounced back in this way. If they bounce in this way, then you will have a situation that you actually going to have certain point, like this point, and this point, they never move. This is continuous generating and continue going to have a refraction wave coming in this way. But at this point, doesn't matter how big this wave is, this point and this point never move. That is what we call the node. If a point in the oscillation that is not moving, that is what we call the node. And what about an anti-node? The anti-node is the point actually give you the most of the movement. So this one is anti-mode, and this one is also an anti-mode. Anti-node, sorry, anti-node. Okay, the last one, brief describe the zero first and second law. The zeroth law is the thermal equilibrium, is the one that we calculate the heat required to change the phase or to change the temperature. The first law of the thermodynamics is talking about the conservation of work and energy. So in that give you an equation, which is the iso process, that is the change of internal energy is equal to the heat from the outside minus the work from the gas to the outside. So it's a Q minus W, and that W is equal to P times change of volume. The second law of the thermodynamics looking at the entropy. So in natural, entropy will tends to increase or stay at zero, maintain at zero. And entropy is a measure of disorder. So if the change of entropy increase, meaning it's getting more disordered. If you want to calculate the entropy, you are going to need to find the change of the heat, which is the Q divided by the average temperature. If you only have one temperature, like isothermal situation, that you only have one temperature, you just use that temperature. If you change temperature from certain degree to another degree, then you have to take the average of these two to be the average temperature that you use for the calculation of this one. All right, I think I finished all this. Ask a question.
Yeah,
And-
it was real helpful.
Okay, I'm gonna stop right now. Let me stop taking.
And one more question, Professor. Is there a lecture today at 1 or no?
No, there's no